So there are three mixing points. So first mixing point, then followed by pump, and it pass through the heat exchanger, then pump, and again second mixing point, and it flow towards the reactor. So exactly the reaction takes place over here. Okay. So now our major task is to make a material balance across each of unit. So to solve this kind of problem, how do we approach? Because multiple units are involved over there. So let's take a simple example. Let's take a simple examples. So we have two units. Okay, it may be distillation column, it may be extraction column, it may be crystallizer, whatever it can be. So this is the feed 1 and this is feed 2, which is getting mixed at this point. So this is the mixing point. And after mixing of both the feeds, it enters into the unit 1 and some process takes place, some reaction takes place, and after the completion of whole process, product 1 is coming out, and the second stream from unit 1, which is also feed for the unit 2. Okay, and before entering into the unit 2, one also side as a byproduct which is also coming out from the unit 1. So, and this is the feed 3 which is entering into the unit 2. So there are two feeds in unit 2. One is from unit 1 and from feed 3. And this is the product 3. So we have product 1, product 2 and product 3 and 3 feed streams. So we need to make a material balance or a component balance across this whole process. Okay. So how do we approach? So first of all, we have to make a overall balance across the complete flow sheet. Okay. So this is a complete flow sheet, and followed by we have to make a hypothetical box across each of unit to understand how much feed is entering and how much product is leaving from that particular unit. Okay. So this is a hypothetical box which represent the complete material balance across the complete process. Okay, and to perform individual material balance, we have to make a separate material balance across each of point. So the second this is the first material balance across the complete flow sheet. The second one is material balance across the mixing point. Okay, because the feed which is flowing in this pipeline, the composition is different. This is the different composition, but after mixing feed 1 and feed 2, the composition of which is entering into the unit 1 will be different, definitely. So that is why we have to make a material balance across this mixing point. Okay. So this is the units. This is the third material balance across unit 1, and this is the fourth one, and this is the last one. Okay. So we have to make a multiple material balance across each of the point where the composition may be changed or where maybe the energy may be changed. The same way we have to perform the energy balance across each unit. Okay. So let's take an example of one example which is not specified. It is a very general example. Okay. Okay. So we have a labeled flow chart of continuous steady state. 2 units process is shown below. Each stream contains 2 components. One is A and another one is B, and in different proportion. And we have to calculate the flow rates M1, M2 and M3 along with their compositions. Okay. So this is the flow chart which is provided, and it is a very general problem. It is not a specified problem. It is a very general problem. Okay. So first of all, we have to try to catch what information is provided. Okay. So the information is provided means this process is steady state. If it is a steady state, so of course there is no accumulation. Okay. And one more thing, it is not mentioned over here. There is no generation and there is no consumption. Of course, no steady state means no accumulation. Okay. So So the next information which is provided in this flow sheet, the unit 1 and unit 2. So for unit 1, this is the input stream having mass flow rate 100 kg per hour, and the components which is A and B, so 0.5 kg of A per kg of feed is flowing, and second one is 0.5 kg of B is also flowing. Okay, and as a output from unit 1, 40 kg per hour is coming out, in which 0.9 kg of A and 0.1 kg of B is coming out. So we have to identify the mass flow rate of M1 which is coming out from the unit 1. Okay. Similarly, the random stream which is getting mixed at this point, we have to which is getting mixed. That is why the composition will change of the M2 stream, and which enters into the unit 2. Okay. So from unit 2 there will be two outputs. One is M3 which is also unknown, and the second output is 30 kg per hour, in which 0.6 kg is A and 0.4 kg is B. So first of all we have to make a material balance. So we have to choose the point where all the information is provided. Okay. So what do you think, which point we have to choose? How many points are there across which we have to make a material balance? How many points are there? As I explained in this part, we have multiple points across which we have to perform the material balance. So I'm considering the same example. So how many points are there across which we have to perform material balance? Feed at mixing point before entering into the unit 1, feed sorry इसे मिक्सिंग नहीं है, गलत बोल दिया, यहाँ पर है मिक्सिंग. हाँ. So first of all we have to make a material balance across the total process. Okay, because the reason is, if we make a material balance across the unit 1, this information is not available with us. Okay, if we make a material balance across this mixing point, so this is also unknown, this is also unknown, of course this is known. Okay, so to it is better to perform material balance across the total unit, because if we perform the material balance across this unit 2, so this is also unknown and this is also unknown, right? Okay, so we have to make a material balance across this total process, and for easier calculation I'm considering the basis which is given flow rates. It is up to you. If you want, you can consider the basis according to your choice, means either 100 kg per hour or maybe 1 kg per hour. It is up to you. Okay, so the information which is not available in this flow sheet, and assuming this the A component which is coming out from the unit 1, which is x1, and of course the B, which is the rest of the part, which is 1 minus x1. Okay, so and the flow rate is m1 kg per hour. Similarly for this unit 2, m2 kg per hour, and the composition is x2, 1 minus x2. Similarly for m3. Okay, so I'm considering the whole means I'm making the hypothetical box, which is I can say the boundary. Okay, now it is very easy to make a material balance across this total unit. So how many streams are coming in and how many streams are going out from the whole process?
3 are coming.
3 are coming and
2 are going.
2 are going. Okay, are you sure 3 are coming?
2 are coming.
2 are coming. So these are the various different units like unit 1, mixing point, unit 2, we need to perform the material balance across these units as well. Okay. So the total material balance is, of course, this is a very general equation which is input, output and generation or maybe something consumption equal to accumulation. So because this is steady state and there is and I'm dealing with non-reactive multiple unit system, okay, which is not reactive. So if it is not reactive system, so generation and consumption will not be there. So this term means the right hand side term and the last two terms will also be get rid of. So these terms will get rid of. Okay, so we have simply input is equal to output. So we have to make a simple material balance across this one. So 100 and plus 30 left hand side and 40 plus 30 and M3. So in this equation only M3 is not available with us. Okay. So with this help, we can calculate the M3, which is 60 kg per hour of product 3, which is coming out from the unit 2. Okay. So followed by we have to make a component balance across the total process, or means total material balance. Okay. So I am considering only component A. Automatically component B will we can calculate. Okay. So the total component balance across the total process. So input is equal to output. So in the input stream 0.5 kg of A is available. Similarly in this stream 0.3 kg is A is available, and the out which is coming out, that is 40. So in 40 this is 0.9 kg is available, and with this 0.6 kg and M3 and X3. So this M3 is known with us, and X3, only the X3 is not available. So it is very easy to calculate the X3, right? Okay. So this is all about the total material balance. Now we have to perform material balance across individual units. Okay. So across unit 1, of course, because at this time we have the information about this input and output stream. Okay. So input, so the 100 kg which is entering as a feed, and 40 kg which is coming out from the unit 1, and the M1 is not available. So we can calculate the M1. Similarly, we can calculate the component of A, which is flowing through the unit 1. Okay. So this is all about the X1, and if X1 means the A, and this is all about the B, which is available after the calculation of X1. Now this information is available, so it is very easy to perform the material balance across this mixing point. Okay, because at this mixing point, this is input stream, this is output stream, and this is also input stream, right? Okay. So the total material balance across the mixing point, which is M1, right, plus 30 and M2. So now M2 is not available with us. M1 we know 60 kg per hour, but M2 is not available. So we can calculate the M2, and similarly we can make a component balance across the mixing point, which is very easy. So this is 0.255 kg of A. So similarly we can calculate the rest of the B. Okay. Now it is very easy to. So in this way we can perform the material balance across each of unit which is available in the process. Okay. So this is all about the material balance across multiple units in non-reactive system and steady state process, right? So I am done. If any questions or any queries, you can ask me freely. Okay. And if you want to attempt, you can attempt this problem. This is also non-reactive multiple units material balance account problem. Okay. Which is also steady state process. So in this problem statement, we design an acetone recovery system having flow sheet shown. All the concentrations shown, both gases and liquids, are specified in weight percentage to make the calculation simpler. Now we have to calculate the stream A, right? Stream A, which is this one, F, which is coming out from the absorber column, W, which is also entering into the absorber column, B, which is coming out from the distillation column, and the D, which is the output of condenser as a distillate. Okay, so this information is available with us. So the same way as we attempt the last problem, you can attempt this problem, but this information is not available with us. So you have to apply a logic key for which point or for which unit we have to make a material balance first. Okay, so it is very easy to perform material balance across the total unit than for attempt individual units, right? So either you can note down or take a photo, and this is tutorial problem for you. Okay, so thank you all.